Hi, welcome to lecture 2. In this lecture we're going to talk about motion at constant velocity. We're going to cover what is this concept of speed and what is speed as opposed to velocity. In daily life we use them kind of interchangeably, but in physics there's a this terminology has a very clear, if somewhat subtle, distinction. We'll talk about how all those concepts are related: time, distance, displacement, speed, velocity. What are the relationships between them? We're going to talk about instantaneous versus average speed. And in the end, last part of this lecture, we're going to start plotting some graphs to illustrate the motion of some object. Then we're going to talk about these position versus time graphs and how I extract the velocity graphically from that. So let's get started. Let's ask the basic question: what is speed? Now you might be saying, okay, I know what speed is. If somebody going 80 miles per hour on the highway, it's different from somebody going 40 miles per hour on the highway. You clearly have an intuitive sense of what we mean by speed. Right? It means to go fast, or the fastness of how you're moving. But let's try to make that precise. So let's imagine you're going 80 miles per hour down the highway. Now doing that does not mean that you are actually going 80 miles for an hour. Right? You're not traveling exactly 1 hour and you've traveled 80 miles. What you actually might be doing, you might be going, let's give some examples, you might be going 40 miles. In MI is miles, because just M is meters, so when you use miles, we don't often do in physics, but right now we are. We say MI for miles. 40 miles in 30 minutes. It's half an hour, right? 40 miles in 30 minutes is the same as 80 miles in 1 hour. It's the same speed. You need to be going 80 miles per hour to go half of that in half the time. Or maybe I'm going 20 miles in 15 minutes. Right? Again, to achieve that, I need to be going 80 miles per hour. When I'm driving in my car, I need to the speedometer needs to show me 80 miles per hour, or else I won't be able to get 20 miles in 15 minutes. Or maybe these are all, ors. So it's this or this or this. Not sure what I just did there. Or maybe I'm going, if I want, how much am I going per minute? It's maybe 1.33 miles in 1 minute. Right, I might be saying I could say I'm going 1.33 miles per minute. That would be the same as 80 miles per hour. It's a different way of expressing the same thing. Or I could write this as 2,146 meters per minute. Again, it's just changing the units from miles to meters. Of course, you need to know how to convert units, and this is a basic skill you need in much of this course. But the point is, all of those different ideas of how you might be moving, 40 miles in 30 minutes, 20 miles in 15 minutes, they all correspond to the same speed. Let's do one more. We might be going, if you do the math, 1/60th of that would be 35.76 meters per second. That's the unit we like to use in most applications in physics. So we're going 35.76 meters in 1 second. That is the same as going 80 miles per hour, regardless of for how long you're actually going or how far you're actually traveling, right? So all of those are the same speed. Right? We're not making a statement about how far you've actually gone. Maybe you've traveled for 20 years in a straight line at 80 miles per hour. Well, you can work out how far you've traveled. But all of those saying I travel 40 miles in 30 minutes, I travel 35.76 meters per second, are expressions of exactly the same thing, just expressed differently. So the same speed. So what is speed then? Speed is a ratio. That's what's the same here. 40 per 30, 20 per 15, 1.33 per 1, or then we can change units to express the same thing. Speed is a ratio, and a ratio it's a fraction mathematically. It's the distance traveled per time taken. And so the same way, 2/4 equals 1/2 equals 15/30. It doesn't matter. These are different ways to express the same fraction. There are different ways to express the same speed. Now, let's suppose I actually want to figure out the distance traveled if I'm going 80 miles per hour. So let's say, suppose I travel 45 minutes at a speed of 80 miles per hour. How far did I get? How far did I travel? Well, in a sense, we don't need to know any kind of equation here. We can just make sense of what it is saying. Well, 45 minutes is 3/4 of 1 hour. If I go 80 in 1 hour, well, I've gone 3/4 of that distance. So 45 minutes is 3/4 of an hour. So I have traveled 3/4 of 80 miles. Keep the units here, miles per hour. I'm just writing this a different way. So then I can, from terms of units, I can actually cancel out the hours here, right? It's like h divided by h. So the units, they work, right, in terms of the math. Put 3/4 times 80, which comes to 60 miles. That makes sense, I hope. Here's just another example of this kind of calculation. Let's suppose I'm riding on my bike. See if I can draw a bike. It's a very strangely drawn bike. Doesn't matter. I'm very bad at drawing bikes. Here we are. This is me on my bike. And I'm going this way at, say, 5 meters per second. You can think about what is that in miles per hour. So I'm going 5 meters per second, m per s, right, meters per second. So I'm doing that for 3 seconds. How far have I gone? How far do I get in 3 seconds? Now, if you don't know anything, like you don't know any math or any, you haven't any physics, just think about it, right? I go 5 meters per second. What does that mean? It means I go 5 meters in the first second, I go 5 meters in the second second, I go 5 meters in the third second. I go 5 meters in the first second, plus I go another 5 meters in the second second, and I go 5 meters in the third second. And so I go a total of 15 meters. Now, of course, I could just have said, oh, it's take the time times the speed. Indeed, that is the way we're going to do this, right? But my distance traveled is 5 meters per second times 3 seconds. You can tell the units make sense. Second per second. Units are gonna cancel out. I'm left with 15 meters. So in a sense, we're going to be using this mathematical relationship that distance traveled is speed times time traveling at that speed. But the point of doing it the slow way, in a way the silly way, is that you see that this equation, if you like, doesn't come from nowhere. It's not something we just make up. It just comes from what we mean by speed. We mean you go 5 meters per second, so you're going to run 5 meters in the first, 5 meters in the second, 5 meters in the third, and you just add those up, and that is your distance traveled. Of course, let's write this down. The distance traveled, oops, you can't see this, is the speed times the time traveled at that speed. I want to write this out because in some situations you might have different times, like you might be going at a certain speed for some time, or you might have a stopwatch that shows you different time. No, it's a time interval or the time period that we've traveled at that speed. I hope that makes sense to you. Okay, so that's the basic notion of speed. Now I want to contrast that with the idea of velocity. Excuse me, velocity. Okay, so here's the crucial distinction, and this is a distinction that we make in physics, right? So when your grandma at dinner table talks about speed and velocity and she gets it wrong, that's okay, unless she talks about it in the context of physics, right? In daily life, speed and velocity kind of mean the same thing, and that's okay. But in physics, they have very specific meanings. And here's the distinction. Everything else follows from that. Speed is distance traveled per time taken, whereas velocity is displacement per time taken. Now hopefully you remember from the previous lecture what the distinction between those two is. If I go from one place to another in a straight line, distance traveled is just the displacement. But if I go from one place somewhere else and back, I might have traveled a large distance, but my final displacement might be very little because I end up close to where I started. If you don't quite remember that, look over your notes from lecture 1. So distance traveled is always going to be positive. I can't travel a negative distance, and so this quantity here is always positive. And in fact, your car, right, shows you the speedometer, shows you the speed, not the velocity. Even if you're driving backwards, it'll show you a positive speed. Meanwhile, velocity could be positive or negative, because displacement can be positive or negative, while distance traveled is only ever positive. Of course, time taken must be positive too. So this part here could be positive or negative, right? Depending on which way are you going relative to your coordinate system. So in fact, the sign of the velocity depends on your choice of coordinate system. Let's write this down. Depends on direction of travel relative to coordinate axes. In fact, we need to generalize a little bit further. It's positive and negative if I can go forwards and backwards, but in more than one dimension, if I can go sideways as well, this actually becomes a vector. So I'm going to put it like this. It's a vector, meaning a magnitude and a direction. We'll talk about those more fairly shortly. If the displacement is in more than one dimension. If motion is in 2D or 3D, so things are moving up and down as well as left and right, or north and south, east and west, and up and down, that would be 3D. What about 4D and 5D? Well, we don't live in a 4 or 5 dimensional space, at least not in any obvious way. And we'll come back to this very soon. For now, we can think of it as being positive or negative, because you can be moving in the same direction as the coordinate axis or in the opposite direction. How are those related? Well, in a sense, speed is the magnitude of the velocity. That is true when we're talking about like this, when I'm not taking turns, when my velocity isn't changing. So let's write this down. If velocity is constant in time, then speed is the magnitude of the velocity. So if I'm going 20 miles per hour north, that would be a velocity because it has a direction and it has a magnitude, right? It's a vector. So displacement involves a definition, expression of direction. I'm going straight north, 20 miles per hour. That would be a velocity. My speed in that case would be 20 miles per hour. And the north sort of just gets shoved under the carpet, right? Don't care about that when we talk about speed. So let's go back to your car. Does your speedometer show speed or velocity? Well, your speedometer doesn't show you whether you're going now north or south or east or west or something in between. It just shows you're going 40 miles per hour. So your car speedometer just shows you a magnitude. It just shows you the speed. Let's look at a couple of examples just to make this distinction clear. So let's imagine I start here. I'm not going to do any artwork now. I'm just going to do little arrows. Suppose I start here. This is my starting point, and I'm going to travel this way. And let's suppose this takes me, this is 12 meters, and I'm going to travel it in 2 seconds. Then I decide to turn around and go back to here, and this is another 6 meters in 1 second. Right, so this is my first leg of my journey, second leg of my journey. So what is the speed? Well, the speed is distance traveled, we abbreviate this, divided by time taken. What's the distance traveled? I traveled 12 meters and I traveled 6 meters. So it's 12 plus 6. Should keep the meters. Divided by how long did it take me? 2 seconds, another 1 second, 3 seconds, 18 over 3. So that is 6 meters per second. That was my speed. My velocity is the displacement per time taken. Now my displacement is where do I end up compared to where do I start. Where do I end up? I end up 6 meters from my starting point. So my displacement is just plus 6 meters. It could be plus or minus, but I'm going to assume my coordinate system starts here maybe and points in this direction. We did the fact that this is my positive axis is the only thing that matters, whether this is plus or minus. So it's in the going from here to here, a distance of 6. When I compare my final position to my initial position, this is 6 meters. It takes me 3 seconds, right? Because that's the time interval I'm looking at over which I'm calculating the velocity. So my velocity in this case would be 2 meters per second. Now, strictly speaking, my velocity at the beginning was, well, 12 meters per 2 seconds, that's 6 meters per second, and then it was a minus 6 meters per second on the second part of the journey. But this is my average, push for an average here, velocity during that time, whereas my speed was just that. My speed changes over time, well, then we really should be talking about the average speed as well. Let's another example. Let's suppose you're driving from Bellingham to Seattle and then back. Right, so it's about a 100-mile trip, more or less. And then back to Bellingham. Right, so that's what we're going to do. So this is about 100 miles, and 100 miles back as well. Well, and say it takes me 2 hours. And I'm not writing this down in some technical way. I'm just making notes of what's going on, right? So don't worry about it. I'm putting this on top of the hour, below the hour. It's totally relevant. I'm just noting down information. I just said in words. 2 hours, 100 miles. That brings me to Seattle. So what's the speed? Again, I should be saying the average speed because, let's be honest, you're not going to go exactly the same speed the whole way. You're probably going to be a lot slower when you hit Everett, where you're going to get into traffic. Whereas a bit further north, the highway tends to be a bit clearer, and you're going to go 80 or 90 or whatever it is that you so recklessly do. But what is the speed? This average speed, well, how far have I traveled? I've traveled 200 miles in 4 hours. So it's 50 miles per hour, or mph, or miles per hour. Doesn't matter how you write it. What is my average velocity? Well, my average velocity, what's my displacement? I ended up where I started. That means my displacement is 0. It took me 4 hours to do it. So this is 0 miles per hour. South, north, well, if it's 0, then I don't really need to specify a direction, because I didn't go anywhere no matter what direction is you're talking about. So let me say this again. Why is this 0? Well, I went 100 miles south, but then I went back 100 miles north. Well, I went 100 miles south, then 100 miles north. Now, I haven't defined a coordinate system, so how can I know what's going on? Well, if you think about it, let's draw a little picture here. So I'm driving down pretty much straight south, and I'm driving back up. Right? Now I could say, okay, let me define a coordinate system. Let me say my origin is here, and my coordinate system points down. Well, then my displacement here would be plus 100, because I'm going in the same direction as the coordinate axis. Then over here it would be minus 100. The total displacement is 0. Somebody else, maybe your friend, lives in Seattle. They put a their coordinate system like this. Well, in which case you went minus 100 displacement first, and then plus 100 displacement, 100 miles displacement later. Doesn't matter. You add them up. Either way, whether you use the green coordinate system or the purple coordinate system, you're going to end up with exactly 0. Of course, the one thing you can't do is you can't change your coordinate system halfway through. You can't decide, I'm going to jump from this one to this one. That will just mess up your math. It's like, imagine you try to measure the length of your yard, but you move the ruler before you walk to the other end. But you're not going to get a sensible answer, right? Same thing here. Or if you measure a time, but then you decide to restart your stopwatch halfway through, well, if you're timing your noodles on the stove, they're going to be overcooked or undercooked or whatever, right? Because you haven't used a consistent, in this case, timing system, or in our case, coordinate system. So let's just clarify a little bit this notion of the average speed and velocity versus the what we call the instantaneous speed or velocity. Okay. Instantaneous velocity versus average velocity. So instantaneous velocity is kind of what you're getting when you're asking, well, how fast are you going right at this instant, like right now, right? So this is what you get when you look at your speedometer. I mean, you get your instantaneous speed, not velocity, as we talked about. But when I look at my speedometer, right, the speed in a car, it tells me you're going 60 miles per hour, and maybe I'm just going 60 miles per hour for a second, or for less. But what I'm getting is this is the speed right now. And if I kept this mode of motion going, if I didn't change the speed, then I would be going 60 miles in an hour. Right? So it's the velocity right now. We call it the instantaneous velocity that will change from one instant to the next. The average velocity is something that's calculated over some given time interval. I can't say what's your average velocity right now. I can say what's your average velocity over the last 10 minutes. Right? Or during the last hour, your average velocity has been 56 miles per hour. Whatever it is, right? whatever the value. So often, like this one is sort of, we calculate this literally by saying, well, how far did I go in what time? Right. This one, I mean, we need a lot more information generally. It's going to be sort of hard to calculate from knowing how far you've gone in a given time unless you're being told, hey, you actually went the same velocity over an extended period. In that case, the two are going to be the same value. So this one here, I said at, 5:32 p.m., 11 seconds, and 0.21 thousandth of a second. So in a sense, you need to specify down to the absolute exact moment in time what instant you mean, and you can ask me what was my instantaneous velocity then. Mathematically, right? Mathematically, a velocity is a distance traveled per time taken. So what we do is we make the time interval, the time taken that we look at, that we analyze, infinitesimally small. Now what does that mean? Infinitesimally means essentially 0 but not quite. It's sort of the opposite of infinite. I'm going to put this in quotation marks. It's like 1 over infinity. That is mathematically ill-defined. But it's saying, I'm just going to imagine it's very, very tiny, and I'm going to imagine I'm always going to make it a bit tinier still in my mind. Right? This is defined mathematically as a limit, and so velocity would be defined as this limit. Let's just write this down, how to do this. So the velocity, I'm just going to write v, is this displacement over time. So the way I might write this is a displacement delta x, right? Displacement per time taken. But then I'm going to say, well, I'm going to let this time interval delta t. So delta t means 2 seconds from 5:32 and 12 seconds to 5:32 and 14 seconds. But I'm going to let this delta t become smaller and smaller and smaller. I'm going to make it 0, but mathematically I'm going to let it approach 0. Now if you're studying this with calculus, then you might recognize this sort of thing from how derivatives are defined. Right, so what this does is, of course, as delta t becomes smaller, the distance traveled in the time also becomes smaller. And so this ratio, even if this is 0, well, this also becomes 0. The ratio is still well defined as a limit. And then I'd use calculus, and I write this as dx dt. Right? Okay. So instantaneous versus average velocity. Now let's see what all of this looks like when we try to illustrate it on a graph. Let's go back to our previous example where we're cycling along. So here's me cycling, and maybe at some instant in time I am cycling past this point here, the way I've drawn it. And at this instant, you standing next to the path, you start your stopwatch. So on your stopwatch right here, it says time equals 0. Well, because I'm going 5 meters per second, we're doing that at a constant, we're not changing that, right? Going at a constant 5 meters per second, I am at, after 1 second, so when your stopwatch shows 1 second, I wrote this as t for time. The time is equal to 0 second, the time is equal to 1 second, time equals 2 seconds, and so on. After 1 second, at this time, you'll see me here. I've moved 5 meters from here to here, or because I'm going 5 meters per second. I'm going to assume I'm cycling in a straight line. So after 2 seconds, you'll see me over here, another 5 meters. And after 3 seconds, when your stopwatch shows 3 seconds, I'm going to be over here. This is a calculation we did earlier, 5 plus 5 plus 5, and so on. So I can now plot this on a graph. So the way we plot those graphs in a way that's useful is we're going to put a time down here. I'm going to put it in seconds, and we're going to put the position over here. So not the distance traveled, but the position. Now let's give it a name. Let's call it x. Of course, to do that, I need to know where is my origin? How do I measure position? So let's do something sensible. Let's suppose I start my origin right here, like it's kind of a starting line. That's when I cycle past it, you press go on your stopwatch. This is also where I start my coordinate system. And this is my x coordinate. I'm going to write it like this. X coordinate, origin here, pointing to the right. Well, at time equals 0, I am at the position x equals 0. So at time equals 0, it's right here. There's going to be 1 second, 2 seconds, 3 seconds, a bit unevenly drawn. Let me fix it a bit. 4 seconds. Right. At 0 time, I'm at position 0, so I'm going to put my data point right here. After 1 second, I'm at this position here. Notice I haven't drawn the bike every time because I'm too lazy to do that. I just drew the one dot that's kind of right in the middle. Right? I'm treating the object as a single point, this particle model that I mentioned before. I'm at 5 meters, so maybe I should put this here. This is going to be in meters. It's going to be 5, 10, 15, 20. So at time equals 1, I'm at 5 meters. At time equals 2 seconds, I'm at 10 meters. So not 5, not another 5, but I'm at position 10. Right, I'm 10 meters from the origin. After 3 seconds, I am 15 meters from the origin in the positive x direction. So that is the data point that I'm going to draw here. Position 15 at 3 seconds. And after 4 seconds, I'm right here. Now, I only drew a couple of those, but you could imagine, what if I had drawn one every half second? Like after half a second, I would have been right in the middle at 2.5. So actually, I could draw this point right here, and so on. If you ask, after 0.1 second, where was I? Well, I would have been at 0.5 meters. 0.1 second, 1/10 of a second. I've traveled 1/10 the distance from here to here. So then I put a little point right here. And if we're going at a constant speed, this graph that I'm going to get looks just like this. A straight line should be going through all the points. Just eyeballed it a little bit. Straight line graph. Now, we could have chosen a different coordinate system. Let's say you start your stopwatch a little bit early, and actually we're going to have our origin right here, so we have a different coordinate system like this. I'll draw it on the same coordinate axes, so you can on the same graph, so you can compare the two. What would the position time graph look for this coordinate system here? Well, at time equals 0, where am I? At position 10 meters to the left, so at minus 10. So I need negative numbers here now. Right, so in this coordinate system, I would have been at minus 10. Then after 1 second, I would have been at, well, I'm 5 meters to the left of my origin. If my origin is here, would have been at minus 5, so it would have been here. After 2 seconds, that's when I finally reach the origin. So I'm here. For 3 seconds, I'm at plus 5, because now I'm over here. The origin is here, so it's 5 meters in the direction that the coordinate axis is pointing. So it'd be like there. After 4 seconds, I'd be 10 meters to the right. It looks like this. Again, I could imagine intermediate places. I just can't draw every single dot. That would just be nonsensical. But the graph I'm getting will just look the same, except the whole graph is shifted down. But they're parallel to each other. Now we can draw position time graphs for all sorts of other examples. But this is the basic ones. This is your straight line, right? If you're going at a constant velocity. Now, if I want to figure out what is my speed, what can I do? Or my velocity. Well, how can I find the velocity from the graph? Well, the velocity is the distance traveled per time taken. So I might say, okay, how fast was I going between 2 and 3 seconds? Well, the distance traveled between 2 and 3 seconds. So first of all, I'm looking at 1 second interval. And the distance traveled in that 1 second, or my displacement rather, if I want velocity, would be plus, let's just write delta x here, but delta t is 1 second. That's the change in time from here to here. That's the interval I chose to look at, somewhat arbitrarily. I could have picked any other time, like from 1 to 2 seconds, whatever else. But from 2 to 3 seconds, that is a 1 second interval, so that's my delta t. Here, the distance traveled is 5 meters. So indeed, my speed is displacement per time, 5 over 1. It's 5 meters per second. Now, graphically, of course, this you might call this rise over run, and so the velocity here is just the slope. Let's write this down. Velocity is the slope of position versus time graph. Okay. Now, if my displacement were negative, I would get a negative slope, right? Because I'm going from positive positions maybe to negative positions. My slope could be pointing down, and I have a negative velocity. And you'll get into examples in class and in the homework where you're working with, some kind of motion that changes. For 2 seconds you might be going here, and then for the next 2 seconds you might be sitting still, and then you might be doing something else. In that case, the graph would take a very different shape. It would have a slope for a certain amount of time, and then it will have a different slope for another amount of time. You'll get to practice all those sorts of scenarios, but we've covered the basics. So thanks for watching, and I'll see you next time.